Without active governance, any shared digital workspace will eventually fracture and drift apart. It is a constant of development. Standard folder conventions and static configuration files fail at scale because they rely on human memory. As a project grows, scripts end up in root folders, dependencies cross paths, and the workspace degrades into a collection of unmanaged files. Reversing this trend requires a shift in perspective. The directory structure can no longer be viewed as a passive storage area. It must be treated as an actively governed data model. Maintaining a pristine development environment requires continuous algorithmic enforcement, a system that monitors and corrects the physical state of the disk in real time. The switch core architecture was designed to provide that specific enforcement. At its center is a mechanism that algorithmically maps every directory and file to a strictly typed schema, defining exactly where every object belongs. This framework is powered by the Multi-File Database Standard, or MFDB, which utilizes structured BJSON files to store the workspace configuration. By implementing an MFDB, the local file system becomes a live, queryable state, allowing the system to track every file with the precision of a database record. SwitchCore uses a centralized orchestrator to read this data and enforce pathing standards, ensuring that physical disk reality matches the intended architecture. Mastering this structure allows teams to govern their local environments with the same rigor as their production codebases, treating the directory tree as a version-controlled automated asset. The process begins by translating the raw contents of the hard drive into a structured database layer. This is the workspace node. Every file and folder in the project is mapped to this entity, which tracks its path, name, and current status. This mapping allows the system to enforce geographic boundaries. For instance, root directories are restricted to core launchers and manifests to keep the project entry point lean. Logic and utility scripts are isolated, routed specifically to the switchcore/system tools directories. Programmatic dependencies follow the same logic, mapped exclusively to the lib/py and lib/sh paths. Even administrative activity is contained, routing all generated logs to a dedicated docs/reports directory. These pathing rules are more than just documentation. They exist as queryable policy entities within the database itself. Each policy record defines a specific jurisdiction and the rule content that the system must satisfy to remain in compliance. By converting these geographic standards into queryable database rows, the system creates rigid boundaries that software can easily interpret and automatically defend. Data alone cannot enforce rules. The database requires an execution engine to act on the information it contains. That engine is the Automation Manager, which serves as the central orchestrator for all background services. When the system initializes, the manager loads the 104a.mfdb.bjson master configuration file to determine the current system state. It specifically looks for the Automation Manager entity to retrieve the operational parameters for the current session. The primary check is for a master system toggle, the automation-enabled switch. If this Boolean is false, the master guard protocol triggers, halting the execution chain immediately. But if true, the manager moves into the service registry phase to identify which background tasks are authorized. This registry maps individual configuration keys directly to the physical background scripts located within the SwitchCore automation directory. The manager iterates through each service, evaluating the individual toggle for each script before authorizing it to run. This logic gate ensures the system only performs tasks that have been explicitly enabled in the database, preventing unmanaged background execution. Once a service is authorized, the Automation Manager dispatches a worker to audit the physical file system. The most critical of these workers is the Policy Enforcer service. The enforcer continually cross-references the physical paths of files on the disk against the entries in the Workspace Node database. If a file path deviates from the parameters defined by the active policies, the enforcer flags the violation for correction. We can see this in practice through the Administrative Docs Retention Policy. The enforcer performs a string matching check on files in the reports directory, ensuring they follow the required this case-year-month-day naming convention. It then validates the file's age, preventing any deletion until a near the 27-day retention period has passed. Through this constant auditing, the policy enforcer ensures that the physical disk remains a perfect reflection of the database schema. This entire sequence is triggered automatically by the user, starting with a basic terminal login. The shell's bash profile calls the initial check, passing control to the automation manager's logic gate. This circular diagram illustrates the result. The orchestrator pulls the configuration from the database and directs the workers to audit the physical file system. This connection between the rules, the engine, and the files creates a continuously self-correcting environment. This closed-loop design identifies and corrects structural drift, preventing the accumulation of the unmanaged entropy that typical file systems allow. A self-healing workspace provides a deterministic foundation where every file location and property is guaranteed by the underlying database. When automated tools navigate this workspace, they can locate dependencies and data with absolute certainty, which eliminates the errors associated with broken or missing paths. This strict geographic governance maintains a pristine state for the system's context window. When an AI agent parses the workspace, a clean context window removes read friction and prevents the hallucinations that occur when an agent encounters misplaced or conflicting files. Algorithmic enforcement over the file system establishes the predictable environment necessary for scaling multi-agent autonomy safely.